ELEC2 2019 question 5. The following diagram shows an incomplete half-wave rectified power supply circuit. A, part 1. The peak value of the transformer secondary voltage VSEC is 21.2 volts. Calculate the RMS value of VSEC. Well, when it comes to RMS, you're either going to divide by root 2 or multiply by root 2. And what you need to remember always is that the RMS value is smaller than the transformer value or the peak value. Therefore, you've got to divide by root 2. So for this particular question, VSEC equals 21.2 divided by root 2. And that gives us an answer of 14.99 volts, or about 15 volts, if you want to round it up. Part 2. Complete the circuit diagram. Well, this is half-wave rectification, and half-wave rectification needs one diode. The diode is always placed at the top and it points to the right. So what you're going to need to do is draw a line across the top attaching the two ends of the circuit. Draw in your diode, making sure that you've got the correct circuit symbol, and then attach the bottom as well. And then the only thing that we need to remember to do is we've got to put in the dots to show that the circuit is attached, and that completes our half-wave rectification circuit. Part 3. Calculate the peak value of the output voltage V0 when the switch is closed. Well, this is the value on the right hand side compared to the left hand side, and you've got that one diode in the middle, and that diode takes 0.7 volts. So V0 is 21.2 minus 0.7, which gives us a value of 20.5 volts. And that is different from the mark scheme if you've checked the mark scheme, but if you look back at legacy papers, it shouldn't be the same as the VSEC value. It should be minus 0.7, or for a full wave rectification you've got to take off 1.4. Okay, part 4. Calculate the ripple voltage when the load current is 0.2 amps. Well, the equation of the data sheet is V ripple is load current divided by frequency times capacitance. Now, we've been given the load current as 0.2. The frequency is back from the circuit diagram. We're told it's 50 Hertz main supply, so that frequency is 50, and it remains as 50 because it's half-wave rectification. And then we've got to multiply it by 1000 microfarads. And this gives us a ripple voltage of 4.0 volts. Right. Part 5. On the axis provided, draw a graph of the voltage V0 when there is a load current of 0.2 amps. The voltage VSEC across the transformer secondary is shown as the dashed line. Okay, so we've got our graph, we've got our dashed line, and there are probably 3 things to remember when you do this type of graph. Firstly, do it in pencil. Don't forget to do it in pencil because it's so easy to make a mistake with these types of graphs, and if you do it in pencil you can rub it out, and only once you're totally happy with it, go over it with a pen. Secondly, you've got to get the graph shape correct. Remember, there are 2 types of graph shape. There are the half-wave rectification when you've got a smoothing capacitor and a load current. You've got the full wave, and this is the half wave, which means that when VSEC is negative, you don't get another positive bump. It just keeps on discharging that capacitor. And finally, and it's just a top tip, make sure that you label key values on these types of graphs. The vast majority of students are not particularly great at drawing graphs, particularly freehand, and it does make a difference if you're showing the examiner exactly what the value should be, just in case your graph isn't accurate enough. Okay, so The key values as far as this is concerned is that the capacitor discharges at the bottom of the ripple down to 16.2. So I'm going to put a dot at 16.2 on the left-hand part of this graph. And then the capacitor charges up to 20.5. In fact, that should be 16.5, not 16.2. Right, and so it goes to 20.5. Then it discharges all the way back down to 16.5 again, charges up to 20.5, discharges down towards 16.5, and it's not going to be 16.5 exactly on the very right hand side, it's still got some way to discharge. So what we need to do is draw a line coming in from the left hand side where the capacitor is discharging back to 16.5. It goes up to 20.5. It then discharges. I'm going to try and draw a little bit of a curve if I can, because it's discharging and it's exponential decay. It then goes back up to 20.5 and then it discharges again down towards 16.5. Now, as I said, it's probably good to label when you get values such as this. So this value here is 20.5 volts, and these values down here are 16.5 volts. And hopefully that should persuade the examiner, just in case my graph isn't totally accurate. Okay, part B. By modifying the power supply as shown, it provides improved line regulation and some load regulation. It uses a 7.5 volt Zener diode. For part 1, complete the definitions for line and load regulation. Now, these definitions you need to know. This question, at least they've given you the starting point. Line regulation is all down to the Zener diode and its impact, and load regulation is to do with the op amp and the rest of the circuit. So, line regulation means that the output voltage of the power supply remains unchanged when? Well, line regulation is all to do when the line voltage changes. So when the line voltage changes. And load regulation is all about the output current or the load current. So it's when the load current changes. Okay, part 2. Write an equation linking the quantities VR, VZ and V0. Well, this is all to do with line regulation, and what we need to do is just give that equation V0 equals VR plus VZ. Right, part 3. Explain how this circuit delivers line regulation. Well, as I mentioned, line regulation is all about the Zener diode, and hopefully you're aware that when the line or supply voltage goes up, the Zener diode voltage stays constant. So what changes? Well, we know from the equation that V0 is VR plus VZ. So if VZ remains constant and V0 increases by 1 volt, that means VR increases by 1 volt. So for our explanation, what we need to do is we need to say as V0 changes, VZ remains constant, and consequently so does Vout. VR changes by the same amount as V0. Now, to try and reiterate that last point, what it's probably good to do in a question such as this, which is worth 2 marks, is to give an example. And so, for example, if V0 increases by 1 volt, so if the line voltage increases by 1 volt, say from 10 volts to 11 volts, VZ will remain constant, and in our particular example, it remains at 7.5, but VR will increase by 1 volt as well. And if you wanted to, you could give those example values. And lastly, for this question, it says calculate the maximum and minimum values of Vout obtained by adjusting the variable resistor. Well, the equation that you need to take from the data sheet is Vout equals VZ bracket 1 plus RF over R1 close bracket. and it's RF which is changing. Now it's a variable resistor, it's a 10k variable resistor, so that would suggest that it goes from 0 ohms to 10 kilo ohms. Now they love this question, and you could almost give the values for this without needing to do the calculation, but what I'm going to do is do the calculation. So what we need to do is talk about those two extremes. So if RF is equal to 0 ohms, then V out is equal to 7.5, 1 plus 0 over 10, and 0 over 10 is 0, so it's 7.5 times 1, so our low value for V out is 7.5 volts. But if RF is 10 kilo ohms, then V out is 7.5, 1 plus 10 over 10 this time, because we've got our maximum value for our 10 kilo ohm variable resistor. And 10 over 10 is 1, 1 plus 1 is 2, so it's 2 times 7.5. So in this particular example, it's 15.0 volts. And given we're not told what the line voltage is, then we've got to assume it's at least 15 volts. So that concludes question 5.